Hello world. Today we shall be dealing with some examples of scalar and vector fields, the gradient and different operations with the operator under the topic Differential Calculus of Vector Fields, the Feynman Lectures of Physics, Volume 2, Chapter 2. Scalar and vector fields. Scalar field is a function which associates a scalar value to every point in space, whereas a vector field is a function which associates a vector to each point in space. For example, temperature, humidity, and pressure. Each of them, when plotted over a graph, associates many directions for a single point. Hence, associates only a magnitude, whereas the velocity of the atom in a rotating object, when plotted over space, results in magnitude pointing towards a single direction, hence is a vector field. As we can see over here, a scalar quantity, pressure, point A, spreads over spreads over a region, hence has many direction for a single point and is a scalar field. And here are some pictorial depiction for scalar field and vectorial field. The del operator. The del operator operates over a function to give us a desired result. The del operator is always hungry to differentiate with respect to something, and one must remember del alone means nothing and t del too has no significance. However, del t gives us a meaningful solution, and one must remember that an operator always operates left side of the function, or an operator gives us a meaningful solution only and only when the function operates at the right side of the operator. Here del equals I del upon del x plus j del upon del y plus k del upon del z, where I, j, k are unit vectors along x, y and z direction, and del is partial derivative. The gradient. The gradient is an operator that operates over a scalar field, and we obtain a vector as a result. The gradient is also called as a slope of a straight line and shows how steep the line is. It is basically connected with tangent. When the line is perpendicular to x-axis, the gradient is undefined. Over a three-dimensional space, the gradient is used to find variation with respect to something. Here, I, j and k are unit vectors along x, y and z axis. The change along x is del h upon del x, the change along y is del h upon del y, and the change along z is del h upon del z. So, the total change along all the directions will be I del h upon del x plus j del h upon del y plus k del h upon del z. One must remember that del v is not equal to v del. It is not commutative. Different operations with del operator. For a better understanding, we need some curiosity. So we ask ourselves, what can we do with the del operator? There are two basic operations that we haven't thought of yet, which is dot and cross product. So del dot h is known as divergence. The divergence operates over a vector function. Here the vector function is h equals I hx plus j hy plus k hz, whereas ijk is unit vectors along x, y and z axis. Hx is the function along x-axis, hy is a function along y-axis, and hz is a function along z-axis. So the divergence operates over a vector function and we obtain a scalar function as a result. Del cross h is known as curl. A curl of a function can be represented as a matrix when solved, results us in a solution in three-dimensional space. It is operated over a vector function to give us a vectorial function. Del dot h equals del hx upon del x plus del hy upon del y plus del hz upon del z. The divergence operates over a vector function and obtains as a scalar function as a solution. Del cross h along the x-axis is del hx upon del y minus del hy upon del z. The curl along y-axis is del hz upon del z minus del hx upon del x. The curl along z-axis is del hy upon del x minus del hy upon del y. When the matrix is solved, we obtain the same result as mentioned before. The mathematical operations that we have studied right now have wide applications in physics. So we shall be taking up the physical significance of these operations and the methods for solving in the next lecture. Any queries are highly appreciated in the comment section. Like and subscribe, and thanks for watching.